Hello? Yes. Okay, can I start? So lecture number 4. Again, I show you again the rationale right behind. So we started out high redshift, intensity mapping, intergalactic medium. Yesterday we saw galaxy clustering, from redshift, let's say 0 up to redshift 1 or so. And now we will be again at redshift 1 or so with weak lensing, and then if there is time about galaxy cluster, I would like to talk also about these objects that are somewhat closer to us, right? So, so the idea is always the same. I will review the basics. For those of you who don't know what I'm talking about, I'll try to be quick. You can also find lectures over the internet. And then I will try to push you at the forefront of this research in terms of fundamental physics, new physics. We know that it is well hidden, unluckily for us. But in the process, maybe we can learn still something about structure formation, nonlinear structure formation, and maybe astrophysics. Some references that I read in order to prepare these lectures. So you can find them, of course, over the slides will be made available to you. So let me show you the first image of a lens quasar. What does it mean? It means that you have these two images, and you do spectroscopy. In 1979, they did spectroscopy, and you have image A and B, and you find that they are pretty much the same, right? They are not identical because the light path will be slightly different, but they are remarkably similar to each other. And actually, let me take a parenthesis that will bring you back to lecture number 2, the IGM. You can use actually this, because this is, of course, the Lyman alpha forest that you might have seen in lecture number 2. And you can compare, for example, these different quasars. So here, there are actually two spectra overplotted on top of each other, but the distance between the two lines of sight is so close, 0.22 kiloparsec, 60 kiloparsec, 265 kiloparsec, and then you start to appreciate notable differences only in this last case here, okay? So you can use this, you can model this, you can have toy models with disks expanded. These are a bit, simple, but analytical, funny. But then you can compare to simulations, and you can really measure this velocity shear by how much, this filament is really kind of sheared, but you say, to modified by the either peculiar velocities that, of course, are taken into account, or the Hubble flow, okay? And exploiting the transfer direction we saw in lecture number 2, it was important for the BAO at very large scales to get rid of the quasar continuum. And here, why is it important? Because the scales that are at play in the high redshift intergalactic medium, which is this spectra here, there are scales that kind of produce suppression of power along the line of sight, thermal velocities, but also in 3D, which is the gas pressure. So this is an effective way to disentangle 1D smoothing, thermal velocities, thermal broadening, to 3D pressure, and then you bring also the word dark matter in, if you wish. Then you can also do word dark matter. So that was a parenthesis. From now on, won't talk about Lyman alpha forest anymore, maybe in the very last slide. So we had these images since, I would say, several years, and this is really beautiful. Last summer happened something really important, right, in the community, which is images got even better, okay? So I was attending a workshop in Sexton when these images came out, and there were lots of people working on strong gravitational lensing, and they felt in just one day their field had moved forward by 50 years, they told me. They were maybe a bit exaggerating, but in the sense that now you really, if you compare the two images, it's not the same object, but now the details of this is really impressive. You find many more images that have been strongly lensed, and so the idea is to do astrophysics, of course, to explore the highest redshift universe, the high redshift galaxies. That's because you can see them because they are lensed by intervening matter. Of course, you can see even farther in time. And so it's important for galaxy formation, but hopefully it will be important also for fundamental physics, right? And there are a couple of applications. One which I'm not going to talk about is that if there are substructures like dark matter halos, they can, produce some granularity. They can destroy these arcs, or maybe produce, in a way, images that are not so neat, so precise. And so this is a set of, a field of research that is really improving over the years, thanks to these images, but also thanks to this ALMA, which gives you radio images which are incredibly resolved, right? Down the resolution is really incredible, arc seconds. So you can look at the same gravitational arcs, both in optical light and in radio. And so you can really constrain your model even further. So weak lensing basics. So we will do optics, right, in the universe. And so we have our metric, of course, in which there is the Newtonian potential. And the assumption is that the gravitational field is weak, the deflection angles are small, so the lens is not very close, the lens is thin and not very close to us, and the deflection happens at scales which are much smaller than the scale of the universe. So there is overall, of course, this principle is very important, and you can use the Fermat principle to basically get the time of arrival of two, let's say, of the light rays. And this time of arrival is related to the gravitational potential. You can write things in this way, where n is a kind of a refraction index, which is produced in this case by the potential, by gravity. Okay, so this is the first thing. And of course, now the goal is to put in relations the actual two angles, right? Which is if this is the source and this is the lens plane and the observer is here, right? You have to put into relationship these two angles, S and O, and you will use this angle alpha here. And so the idea is that if there hadn't been any lens, this thing would have been gone this way, the light ray, but there is a lens which actually produces this path. And we know that the photons will follow a path for which the light travel time is stationary to small changes in the path. This is the Fermat principle, okay? So you do optics, you can write this alpha angle like this, put it in relation with the potential. The potential is modeled like this. This is the mass in the lens. Of course, there could be also intervening matter here and here, but for now we don't take it into account, we just integrate him here. And this is a relationship between the alpha angle and the actual projected density of your lens. So this is fairly established, but put it a bit more in the context of getting the so-called lens equation. This is what you have. You have the source plane, you have the lens plane, and this is the observer. And here is really simple to deal with this equation here, right? It's really very simple geometrical arguments that you can dig out by yourself. It's straightforward, but basically the final goal is to put in relation this beta, which is the angle of the source to the source between the observer and the source plane, to to alpha and theta, right? And alpha will be also a function of theta here, okay? So it's really simple, right? You can do it yourself. And this really governs the light path. This is the so-called lens equation. The mapping, so this is what usually said, the mapping from image to the source plane, from image to source plane is easy. And this is the not case for obtaining the mapping from the source to the image plane. A source with true position will be observed at all positions that satisfy the lens equations, in principle, if the problem is simple, right? There could be other sources nearby, there could be gas, mass distributed not in a point-like way, and so, but in principle, this is easy, and this equation will cause the Einstein rings, caustics, so multiple solutions. And so people use this actually to get H naught, as we will see later. Another set of definitions, the same quantity but be defined differently. We will define convergence, which is an adimensional quantity, which is the projected mass over this projected surface density casted in this way, critical density, so this is adimensional. The deflection angle, once you bring this in, will read like this, and basically this can be defined as the divergence of the gravitational potential, right, of the lens, gravitational lens potential. And at the end of the day, you will find the consistency relationship between these two things, the convergence of your system and the gravitational potential, which is a Poisson-like equation, right? So for this kind of business, what you really need to know the redshift of the source. You need to really to know these things, and you would like to have spectroscopy to be precise, because with spectroscopy you know things much better than with photometry, and so you know that spectroscopy is expensive while photometry is not. So you can do this trick only for few objects, right? Because these systems are rare, and there are not that many. While we will see later that you can do photometry for getting this K. The convergence at cosmological scale, that will be a different set of questions. So the question number one, we are in a strong lensing regime. We can look at the delays of light path from the source to the observer. This is the lens. You will have generically two different light paths, or maybe three, like in this case, or even four actually. And you should model this. You can be aggressive or not in modeling this. It depends a bit on your personal attitude. But at the end of the day, you can find light curves that are being observed of this distance source, and they look remarkably similar, and they will arrive with the delay. And so the level of sophistication of this kind of studies is nowadays withstanding, I would say, because people, for example, they observe, I don't know, some light appearing here, B maybe, A, and then they get prediction. They will say, you know, in few months you will have something popping out in the image over there. Okay, so, and typically they get it right, and in doing so they learn a lot about the gravitational potential. So here is what we have here is basically we cast these time delays in terms of this. Sometimes it's called tau, but here it's called phi. I don't know why actually, but it's the so-called Fermat potential, which is a scalar function, which depends on a geometrical part, which relates the angles, the two angles, theta and beta. And this minus psi is something that will cause the slowing down and is determined by the potential at the source place, right? At the source position. The units of this is angle square, and so it's the first thing that you can look at, right? Once you have the length equation, basically the first thing that you can look at is really the time delays, and then you take derivatives, and you will get to higher order effects, deflection, distortion, that maybe are more interesting for cosmology. Fairly established, slide number 2. So again, this is the difference in the Fermat potential. This D at T. How do you work this thing out? You should know D and S, the position of the source and the length. You should assume a cosmological model or marginalize over, and you get all these terms here. Then you measure delta T, right? And you also assume something for the potential. And once you get this, you will see that this will scale as 1 over h naught, right? And so you can measure things. So the problem is that one of the problems is that this projected density at the lens position it doesn't have a unique solution. Okay, so you can rescale things in such a way that this is an equally good solution to your equations. You scale the beta angle, and you scale this by adding a uniform mass sheet in front, and you'll get something that slightly changes linearly, actually, your Hubble constant. This is something that Kfir will talk about, hopefully. And anyway, this is something that people did recently to get, you know, an independent way of measuring h naught. And what they get a few years ago, this is maybe holy cow 3 years ago, is this number here, if I'm not mistaken, because I'm partly colorblind. Maybe it's this. Yes, it's this one. And so you see, it's on the high side, and this one is the Planck value. So it tends to corroborate, let's say, the values that you obtain by supernovae plus anchored with local Cepheids. So the error bars is tiny, and one of the reasons why this error bar is so tiny, 2.44% error, is that they assume a specific model for the potential at the lens position. If you go non-parametric, people like Castorina, Kfir, Bloom, shown that these things get relaxed. And after they saw this paper, they also got relaxed in the modeling of the gravitational potential, and the error bars went from 2 to 8%, 74 plus minus 6. And if the error bars is like this, is more conservative, of course, then you cannot really tell which is correct between these two measurements, right? Between the supernovae and Planck. So then the point I want to make here that this strong lensing, when you use it in terms of time delays, it will offer you opportunity to measure h naught. But there are some assumptions, like always in physics, as we heard before. So now we take the first derivative, right, of the lens equation, basically. And with the first derivative, we have deflection of light rays due to intervening mass. And it has the units of an angle. So this is the equation that we saw before, just the first derivative of this. And we have a notable example of this with the CMB, right? The CMB is lensed. And this lensing is small, is of the order of few arc minutes, but it also produces a pattern in the TT. So it's measured very well by the CMB, and it can be coded up in this way. This is this is a kernel which modulates the effect of the intervening matter, and is a kernel which is quite broad, and actually in terms of redshift, right? So we will not talk about this, but it's an effect which is present. You should remember this. What we are mostly interested in is distortion, okay? Distortion of images. So let's look at this first. If an image is perfectly circular, what this effect is describing is the change of this image into an ellipse, okay? And this is called the shear, but also there is an effect of magnification or demagnification of the photons, which is coded by this matrix. Actually, this matrix codes both the effect, and this, in general, you should expect, right, a change in size of this image, but also a distortion. So you can describe this, you can measure this new image, and the assumption is that the modification is induced by the intervening matter, and then you can go back and check whether or not you can recover the intervening matter distribution, which is the convergence, right? And so the goal of this equation is to put it in touch together, to provide a connection between what? Between the convergence that we saw before and this gamma function, which parameterizes, basically, parameterizes the change in shape, right? And, well, there are some assumptions here. This describes the magnification. You can see that you have kappa entering the convergence and gamma, the modulus of gamma. And also the reduced shear is a definition. It's related to the shear in this way. And also here, what you have here is B over E, A, the ratio of the two ellipse axes. They are related to they are a function of the modulus of the reduced shear, okay? The units of this is a scalar. Okay. This is the derivative of beta, right? And this is the derivative of the modulus of the derivative of beta. So it's effectively a distortion matrix that you parameterize. And actually, the point to make here is that the shear is a spin-2 quantity. It needs to be described with two vectors, and you like to describe this typically by taking the imaginary part, right? So we will see this later. So, in general, distortion produces two effects, right? One is that the true survey area is changed, is really a volume effect, if you wish. And the second one is that objects becomes brighter, typically, because, you know, the paths are more converging. So these things have been known since ages, that the actual number density of sources as a function of magnitude or luminosities, if this is the intrinsic, if this is the correct one, is reduced in volume and can be increased in flux, so it changes shape, right? This function here changes shape because of this effect. We know this. So in practice, people, as I said, they want to check, they want to model the relationship between gamma and kappa, right? That's the idea. And so if you write the the Poisson potential like this is the convergence, this is the angle, this is the equation that we saw already before. Then you model gamma 1 and gamma 2, the two shear components in this way. Then you can do things in real space or in Fourier space. It's up to you. You can do both, right? People tend to prefer this one. And what you find out is that the modulation between gamma as a function of the angle, theta, is modulated with kappa times a kind of distortion kernel function, which depends on actually theta 1 and theta 2, which describe the change of shape, right, of your image. In Fourier space, things read a bit more simpler, at least on the mathematical point of view. They read like this. And again, of course, the two, they must be consistent, right? And indeed they are, times this kappa 0, sorry, which is related, of course, to the mass sheet degeneracy. So we want to describe now this gamma field. And the procedure is similar, if you wish, to the B modes of the CMB, right? You have a spin-2 field, and you should describe its orientation. You describe it with gamma 1, gamma 2, and a phase, which describe this. And then you can also cast things in this way, and casting things in terms of real function E and B, epsilon and beta. And epsilon is parity even, and beta is parity odd. And this is fairly established. And then what is this? Basically, shear can be decomposed in two modes. The E mode, which is the so-called tangential shear, describes the change of the images in this way. And this one is the B mode, which is not very important. We change the images in this way. It's called swirling around overdensity. Here you have to think as if there is an overdensity here, a little bit like the CMB. And so the idea is to measure the tangential shear out statistically in the sky and get to know something about the matter distribution. And people did this, right? This is an example. This is the tangential shear. And if you write things down, it is effectively a mass density contrast, okay? Where this is the average kappa, the average convergence. This is what you actually measure, right? So it's the mass contrast. It's the local measurement, right? and it's really estimated by using projected mass quantity within a radius, and you should make, of course, few assumptions about the radial distribution. So we saw something which is relevant, but of course the other thing that you could do is maybe you can also write the power spectrum of kappa. It reads like this, and this is a very important equation because it relates what? It relates kappa to basically this power spectrum of kappa to the power spectrum of density perturbation. And this is very important in contrast with galaxy cluster. This is the nonlinear one. Okay, so it's very important to stress this because it doesn't really care about linear or nonlinear. It's mass, projected mass, and so this is modulated by some kernel function which relates to the distribution of sources, lenses, which is in case are over density which are changing, right, producing the convergence. And people know these things since many, many years, actually. And the first studies, they were modeling this nonlinear power spectrum in the context of Halo model. In this case, this is the nonlinear convergence power spectrum, kappa, and it's modeled within one Halo term, which is, I guess, this one here, this one here, and then two Halo term, which is not important here. And this is probably the shot noise due to the discrete number of sources that you have. So this is to establish, right, the basics. So luckily, we are in a fortunate position that the number of weak lensing surveys has increased dramatically in the last 20 years, so actually 15 years. So we started with these surveys like Cosmos, CFICH, TLS. Then we had KIDS. This is the observed galaxy density per arc minute. So you see that it increases the number of gradually. But also, most importantly, the surveyed area increases from 2 degrees, 2005. Now we have, where is this? It's here, 5,000 square degrees. And Euclid, hopefully next year, 15,000 square degree. Rubin telescope, Roman telescope will go even farther, right? So here it's important to beat down the shot noise, to have many more sources. Here it's important to be statistically more, let's say, richer in terms of statistical area surveyed. And I think that the forefront of this in terms of cosmology, there is DES, and these are the latest results which came out recently. It's an imaging camera placed in Chile. They observe the sky in 5 imaging bands, and they do photometry. They don't do spectroscopy. So what does it mean? It means that they don't know the actual position of their sources. They cannot be extremely precise, but for lensing is good. Their quantity, lensing anyway projects, and the sources are also projected, so somehow you don't face these problems of modeling the bias at k equal 0.3, 0.4 with effective field theory, the large scale structure, putting in the counter terms, the extra term. You don't face this. You can be more, in a way, more relaxed under the modeling of the distribution of your sources because you have this effective way of filtering the signal with the window function provided by the DNDZ. This is the slides from Martin Croce, who was last week in Trieste. 5,000 square degrees. You have also some deep fields to check systematics. So this is what they're after, of course, a statistical measure of the E mode, right? And of course, in reality, you have mass over density, right, which create this tangential shear, but you also have under density. And so at the end, what you are after is the correlation function of shapes of galaxies, right? You measure, this is the ellipticity of the galaxy, you measure this, and you typically, this again, a vector, you decompose it in tangential and radial, and you get this cross-correlation function that you can cross-correlate in theta angle, but also in beam by beam, right? And that's what they do, we will see in a second. These are the effective window function for the sources. So out of this is nice because it provides a bit of connection with the previous lecture. You can do 3 things, because you have the shear and you have the galaxy. The first thing you can do, look at the cosmic shear, and so you have the tangential and the radial. This will be a signal in general proportional to sigma 8 square, and so you have correlation function in real space. Then you also have, forget about the shear, you have the galaxy, right? And you can do galaxy clustering, and this will of course depend on the bias of the galaxies, and will also depend on the power spectrum square. But also you can do galaxy, cross-correlate the galaxy with the lensing, with the galaxy lensing. So it's basically the cross between these two, and that will scale as b sigma 8 square. So basically you have, constraining power from a set of 3 different physical quantities that you extract from the same area of the sky, from the same volume of the sky. And of course, the nice thing is that to see whether or not they are consistent with each other, right? Because if they're not, there is something wrong going on. And effectively, they are dealing with, these quantities. This is, let's say, this data vector will describe the autocorrelation function of galaxies. This one will describe the lensing signal, and this will describe the galaxy lensing cross-correlation. What are the G0, G2, and G4? These are analytical functions. They are tabulated in this paper here, STEM is 1996. They take into account the projection of the signal on the sky. It's purely geometrical, it's analytical. And so at the end, they have this data vector, which is really huge in a way, right? And you have to model this and see whether or not this is consistent with the data. So why is that weak lensing is so appealing, is so nice? Because so far, I didn't show you any dirty detail, right? Everything looks mathematically beautiful. Optics in the universe and a little bit of mathematical potential. In reality, things are a bit different, right? So I put this cartoon here because of course, people have been working on these things, not myself in person, but people have been working on these things since a long time. And so at some point, if you want to discover neutrino mass, you have to deal with systematics. And this is just a set which is probably not comprehensive of the systematics you're after, right? The galaxy bias, is it linear? Should you have extra term like EFT people do? Galaxies are also intrinsically aligned. This is a very important systematics. Why is that? Suppose, for example, you take some, I don't know, very much you select for some reason star-forming galaxies. They are shiny a lot. They produce lots of stars. It could well be that they are an intersection of the filaments, so they have a given ellipticity. While if you take them passive galaxies, maybe they have already exhausted their gas, and they are maybe aligned to the tidal field of these filaments. So this is something to care about. Why? Because the intrinsic ellipticity of a galaxy is of the order of 0.3, while we are after at a signal which is much, much weaker, okay? So the hope is that statistically you will be averaging out all these galaxies and you will get the cosmological signal. That's really the hope of these people. And what else? Of course, you need the shape of the galaxy. Estimating the shape of the galaxy is not that easy. You see here they degrade the images with software that you can also find, they're public available. And at the end, you're dealing with this, and you want to really, the real image is this one. Then there is seeing, that we know what it is, right? That's why telescopes are built in the Canary Island and not in other places of the world. And you see, in bad seeing, it's difficult to observe a shape and ellipticity. Good seeing is, of course, better. And then what else? Galaxy image can blend, blending also of photometric rashes, so you cannot really tell, projection effect. Then also, this thing condition will change with time. And also, yes, the point is that I want to make is also these things, they propagate out at large scales, right, somehow. So in the sense, it might look to you as if it is a small scale effect you don't really care about, right? But in reality, if you make the same mistakes many times, at the end, you will get spurious correlation of these ellipticities at the scales they are interested in. So people in the desk collaboration, which I'm not part of, I think they did a very careful job. And the thing that I like most is this one. So this is, again, what is this? This is cosmic shear, autocorrelation lensing, cross and galaxy clustering. What I like most is this shaded area here, which is areas that also don't want to model. So in principle, there are, you see, lots of points with very small error bars. They say we don't want to model this because these scales are too nonlinear for us, and we are not sure that the nonlinearities in theoretical modeling are good enough, right? And maybe you can be aggressive and see what happens if you use those in the analysis, but the attitude is to be conservative, which I like. So what do they get at the end? If you remember yesterday, I showed you this S capital 8, which is a combination of sigma 8 and omega matter, and they measure this quantity here. Why they measure this quantity? Because basically sigma 8 and omega matter for this measurement is correlated. And so they want to cast a physical quantity which is not correlated, right? A combination of the two that is kind of better measured. If there are no correlation, it's just a ball like this in the plane, but if there is correlation, it becomes a banana. And they measure this, and you see this as a function sorry, but this is probably, that is really sigma 8. Sorry, this is a type, I guess. It's sigma 8 because it's a function of omega matter, probably. And so you see, the point that this plot makes is that if you consider autocorrelation of galaxies and cross-correlation galaxy lensing, this is perfectly consistent with the lensing signal. So in a way, you see the overlap between these 1 sigma and 2 sigma contours is really substantial. So it's really telling them that they are probably on the right path and there are not strange systematics. And they get S8, sorry, this S8 is really S8. And what did they get? This S8 in lambda CDM is this, omega matter is this, and the sigma 8, which is derived quantity, is this, okay? What is the tension with Planck? Well, maybe we can see it later, what it is, because it's a factor of 2 improvement compared to the first year data release. In WCDM, if you relax W, you don't make it equal to -1, but you let it free. Omega matter increases, but only slightly so, right? By a few percent, not substantially. This is also, I guess, an unexpected finding. What did they do also? They split between high redshift and low redshift. They made many consistency checks. They have this p-value is a statistic which kind of summarizes how likely this measurement is going to be in the context always of Bayesian statistics and MCMC, Monte Carlo Markov chain. But again, here they compare with Planck, CMB only. And so you see, once you combine Planck and this dark depth measurement, you are in this region. So the two measurements, they touch each other at 1 sigma. So the kind of, you know, if you consider cosmic shear only, you have a tension of 2.1 sigma, but once you complement cosmic shear with galaxy clustering and the cross, bam, they are on top of each other. So there is no really tension. The other thing that they look at is that if you assume a prior, a BBM prior, you can also check out of this data H naught. And again, they get a value which is in agreement with Planck. Okay, so what they use? They use baryonic acoustic oscillations, BBN, and these measurements, no CMB, okay, in this case, even though they must assume something for the RD, the sound horizon, and they get this number here. So again, this is kind of hinting to the fact that they are supporting the H0 value of Planck. Neutrino masses, upper limit 0.13 electron volt. This is a number that you saw often, right? It's kind of the ballpark of all the other numbers, so no surprises from this observable. These are, again, consistency checks. We can read, we can not pay too much attention. Dark energy, again. So what do you see here? This is DES only. You see very wide 1 sigma and 2 sigma. You add BAO, redshift space distortion, supernovae, you end up here. So you really by putting kind of external constraints, you get really here. Planck, we know, Planck alone doesn't tell us anything about this. So here the point that I want to make is that if you forget about the CMB for a second, and if you use just this low redshift data complemented by BAO, RSD, and supernovae, you get really kind of, you know, cornered in the region of the parameter space in which there is no room for, let's say, an evolution of the equation of state of the dark energy. This is WAW0, this is WAWP with WP a pivot, which is a 0.3, where most of the data are sensitive to. This is neutrinos. Well, let me skip this. Modification of gravity, we just saw before, right? This mu function and sigma 0 function. And also they can be constrained by this data. Again, sigma 0 and mu 0, which are related to eta, of course, they are on top of the standard GR case. And how do they get these numbers here? Because they are also sensitive to growth, and they also can split up the sigma 8, the recover sigma 8 in beams where the galaxies are, right? They have 4 beams, and they measure sigma z at the different beams. They typically lie on the low side compared to Planck. So let me tell you something important. DES is not the only weak lensing survey that we have. There is also KIDS, and KIDS is getting something which is a bit different, which is of course of interest for us. And the same plot for KIDS is a bit different because it's a bit low. You see, this is Planck, S8 omega matter, capital S8, and Planck is here, and the data tend to be down here. The tension is now, this paper came out by Catherine Hymans, I guess last year, 2021, and now the tension between the weak lensing of KIDS and Planck is at the level of 2-3 sigma. Okay? And this tension is not solved by any new physics that we are aware of. Okay, so what do they do? So basically what's happening here, again, nonlinear power spectrum, weak lensing data in small scale, nonlinear scales. They seem to have smaller sigma 8. What could be the reason for that? One reason that they are advocating is the so-called baryonic correction. What does it mean, baryonic correction? It means that baryons are not just passive traces of the dark matter. Baryons interact gravitationally with the dark matter, and if you have complex astrophysical aspects like galactic feedback, the galactic feedback, which can be produced by AGN or by stars, by supernovae, they drive wind, they have pressure radiation, they drive the baryons out of the potential well, and the baryons, they back react gravitationally with the dark matter, and they cause dark matter suppression. This is very well established with simulations by several years. And so what you see, for example, here is the power spectrum in harmonic space of, these are just models in which you have baryonic corrections, okay, and models in which there is only dark matter. And this is L. Large L means small scales, small L means large scales. So what you see here, look at this plot here. This is a model in which you have baryonic feedback, in which basically you do the following. There are two parameters governing the model. Eta B, which tells you how much the feedback is efficient, how much these winds are capable of removing gas. And this MC parameterizes the mass at which this feedback mechanism starts to be relevant. We know that the small mass halos are not very active under this point of view, and so these halos will just have no feedback, but halos above mass 10 to the 13, 10 to the 14, 3 times to the 14, they can eject, maybe through the AGN activity or through winds, right? This is purely phenomenological, but it's based on many hydrodynamical simulations, TNG, LUS, that you might have heard of. And here you see the suppression of power, right? The suppression of power goes in the right direction. It suppresses power, as the name says. And here in this nice paper, we asked ourselves, is there an interplay between this suppression and maybe the presence of the neutrino? Neutrino, we know, neutrino free streaming case is suppression of power. If you look at the plots, right, it seems the neutrino suppression is a bit different. It starts much earlier. It's a bit more gentle, right, while this one happens at somewhat smaller scales and is a little bit more abrupt. And so what is the rationale behind? The rationale is that maybe to explain these kids' results, maybe one can have a bit of both, right? One can have a little bit of neutrino effect, a little bit of this, and then you can ease the tension. People check this, doesn't really work. Why does it really work? Because, I mean, this is shown just at one redshift, but if you let the redshift free, the two become independent from each other, and the data are very much constraining, and so they help a bit, but they don't ease the tension. So, and it's a bit tricky to get the things correct. So I think we cannot. We should also mention galaxy clusters, right? How many minutes do I have? Something like 10. Okay, perfect timing. So there is also some cosmology actually that you can do with galaxy clusters. And the thing that you can do is to count them, the easiest thing that you can do, and see whether your expectation matches the theory predictions, right? Your measurements matches the theory. And how do you count cluster? Well, you can observe it in the optical, you can look at them with weak lensing, you can look at them with X-rays, you should find some tracers. And the tracers of galaxy clusters are astrophysical processes, right? You select them by looking at some astrophysical processes. If you are in the optical, you will be looking for concentration of galaxies clumped together under the same gravitational potential of about 1,000 galaxies. Their dispersion velocity is rather large. The size is 1-2 megaparsec. The mass is 10 to the 15. And this should be, you know, if you work out the numbers, this should be produced by the gravitational, this object, by the gravitational collapse of patches of 10 co-moving megaparsec, right? They detach from common expansion, then they collapse. The baryonic content is about 15% of the cosmic budget, if you assume hydrostatic equilibrium. But then you can also look at them in the X-rays, and in that case you observe an ICM temperature. You observe the intracluster medium, which has its own temperature. The temperature is so hot because there are physical processes like thermal breast round, they are heating the things up and keeping this level of ionization and with this luminosity. So this is the usual problem, right? How to really convert let's say properties that you see to the mass of the halo that in order to do cosmology. The other way is to look at SZ cluster to the Sunyaev-Zeldovich. I'm sure you have heard of this, right? This is the inverse Compton scattering of CMB photons out of on top of free electrons, which are in the intercluster medium, and this is well established since ages. And so you see really, you know, blobs like this one, and so basically this allows contrary to X-rays, which are more sensitive to large mass, the high mass tail of this galaxy cluster. With this SZ, you are probing, let's say, more also on a wider range the cluster galaxy function, right? Now we are more, let's say, pushed towards this kind of system because there are a bit more experiment, even if there is Rosita, which is taking X-ray data. So we would like to know soon, hopefully soon, whether the two are consistent with each other. So, as I told you, we want to count them. So when you count them, you can write the number as a function of logarithmic mean of mass. And this is parameterized as a function of M200, which is the virial mass, let's say, of these halos. And these are theory predictions for this evolution of this mass function with redshift. It's based on Press-Schechter. And you see that if you keep this quantity constant, you will end up on the very same line. So this is an intrinsic degeneracy. And it's telling you that mass function is probing this parameter combination. You are sensitive a bit to the amplitude and a bit to the shape. Unfortunately, not only that, because you will be the redshift evolution will change things in this way. And also sigma 8 omega matter are sensed this way. The mass, if you get the mass wrong, you will be moving things in this direction. And the selection function is also a very important quantity. Will tend to move things in this direction. So at the end of the day, your cosmological information is going to be, a kind of integral over your final observed quantity is an integral of the cosmological information time a probability they observe an object of that given mass at that given redshift, which will be very complex, right? Because it's intimately connected with the astrophysics, with how much light traces matter. And then on top of this, you have this selection function on top, and the volume which is actually surveyed by your typical survey. Okay, so but anyway, this equation is relatively simple, and there are some caveats, right? So I told you before that you have to think in galaxy clusters in these terms. At some point, you have this patch of 10 megaparsec. It kind of starts forming this big cluster, so they detach for cosmic expansion, and so it's kind of reasonable, right? That they have in their kind of patch, in this patch of 10 megaparsec, you have a cosmic budget which is close an omega baryon value which is close or equal, let's say, to the CMB1, to the BBN1. No? So this gas is there. Other gas cannot enter anymore. The only thing that can happen in this gas, and indeed it happens, is going to be turned into stars. You will star formation, galaxy formation. And so people did that. What do? They measured out of X-ray data, people like Steve Allen, other people, they measured the gas fraction. It's relatively easy, right, out of X-ray data, because also you assume hydrostatic equilibrium. And they modulate this with a function, capital gamma times the cosmic value. And this function here is measured from simulations. Can be parameterized like this with some freedom, right? Gamma 0, gamma 1, and alpha. And they now compare with the data. And they get basically out of this F gas, they get the mass. And the mass gets the mass function, right? You can do cosmology. You can see really how this quantity is observed is related to cosmology. And the nice thing, again, is this one, that once you try to combine several probes, they have all very different degeneracy line, and at the end of the day, they overlap in a region of the parameter space, which is really omega 0.3, W equal -1. So it's the Planck case, right? So this is month 2021. You use the gas fraction to do cosmology. The other thing is using optical clusters from this red mapper SDSS. So you use optical light. And what you get here is this number here, 7,000 clusters. You get this here, okay? And this is Planck, 2 data releases, and this is the BAO value, yes. And so they kind of agree with each other. So before gas fraction agrees with Planck, optical galaxy cluster, they agree with Planck, with CMB constraints and constraints for other clusters galaxies. So this one is a bit different in the sense that in this case you don't agree that much, right? This is using SPT-SZ survey. It's a bit on the low side, omega matter. Sigma 8 may be in agreement. And this is 400 clusters supplemented by constraints on this on these clusters, also using weak lensing and X-ray observations. And these are the contour. Planck is Planck, of course. Kids and gamma is weak lensing. This is Wade the Giants program is a survey of galaxy cluster. This is SPT cluster, and this is DES 1 year. And you see here in terms of growth, sigma 8 as a function of z, the data are slightly below. This one here is completely off, right? This one is the DES. DES has somewhat constraints on from galaxy cluster that are a bit strange at the moment and are probably hampered by systematics. So at the end, sigma 8 at omega matter, when omega matter is fixed, from, you see, X-ray cluster, SZ cluster, optical cluster, weak lensing, CMB, it seems to provide, for most cases, a kind of consistent story. We are sigma 8.8. This one is a bit off, right? This is the 1 sigma into sigma by... this is the combined. This one sigma into sigma is the combined measurements. So the other thing that I want to, and I'm nearly done, is also to provide the connection with the first, the second lecture with the IGM. So with Matteo Esposito, who is a student at MPA, what we did is basically compare the sigma 8 derived from SPT galaxy clusters and Lyman alpha. And if you see sigma 8 here as a function of matter, they don't touch each other, the two islands, right? The two posteriors. In one case is 0.9, in the other case is 0.75. And so what we did, of course, you cannot combine such two observables, right? Because they are in tension, it will be silly to do so. But what we did was saying, okay, let's suppose for a second that Lyman alpha is correct, and you enter in the likelihood of the galaxy clusters with the cosmological parameter of Lyman alpha, and you ask yourself what is the things that have to change in terms of bringing the two into agreement. And what has to change is this function here, which relates basically the mass of the halo to the observed quantity, which is basically the relationship between, let's say, the SZ effect that you observe and the mass, okay? And so it's telling you that if you want to bring these two into agreement, you have to really, you will end up with two different relationships between the SZ cluster mass estimate in the two cases, right? So you have to have your mass wrong by, you can read it off here, by a factor of, let's say, a few, right? If you want to go from here to here, instead of 10 to the 14, it has to be a few times 10 to the 7 to 10 to the 13. And apparently this is very unlikely. So it's something we can speculate on whether there is new physics. I remind you, galaxy clusters redshift 0.3, 0.2. Lyman alpha is at redshift 3. So maybe it's a tension, maybe it's new physics, maybe some systematics. Let me conclude with this slide. So it was a quick, journey into weak gravitational lensing, and it's very important, an exciting cosmological probe, which have kind of reached enormous achievements in the last decades or so, due to the fact that you have more data, more people, clever people working on the systematics. And so I believe there are, of course, gray areas in which some results are a bit contrived, are a bit difficult to interpret, but nevertheless is again another test of structural formation at a different epoch of the universe. Some sigma 8 tension seems to be present, especially when considered the Kids weak lensing dataset. Also, I show you that in terms of, there was a little bit of tension with the Lyman alpha forest, and the future, again, hopefully, is bright. Euclid will be launched in a few months from now, and we do have LSST Rubin, of course, it's going to be very important. eRosita, hopefully, will provide us with some galaxy cluster catalog, and then we have Roman telescope. So I'm sure that there could be breakthrough in terms of, further constraining theories, like beyond lambda CDM, maybe constraining a bit further the neutrino mass, or even discover the neutrino mass, or find out whether W can be different from -1. Thank you. There was...
Again, quick curiosity
Yes.
about the last slide on Lyman alpha versus class. Like, what data set did you use for the Lyman alpha?
We use the high redshift data KEC IRES, so it's a kind of small scales. We didn't use the slow and low resolution.
Yeah, because I remember there was this paper by Julian and Nils and Palantel where they found that for EBOS, sigma 8 is kind of compatible with weak lensing. So is there maybe a contradiction between Lyman alpha datasets?
Yes, indeed. The sigma 8 value of the low resolution Lyman alpha data is a bit on the lower side compared to this. So the tension is maybe at the level of 2 sigma or a bit less. So there is no really real tension. Yes, you're right. Yeah.
Okay, so I have a question about the constraining on H naught that you showed.
From the from what? From the time delays or from the weak lens?
It was BAO combined with weak lensing, combined with BBN priors.
This one maybe.
Yes.
Yes. Maybe this one. Yeah.
So I was a bit confused because essentially weak lensing doesn't constrain H naught at all, right? And
Exactly.
BAO isolated from some prior on the sound horizon doesn't either, right? So
No, okay. So there is here a prior on the sound horizon, and the prior on omega baryon. So BBN means omega baryon is fixed somehow. But so it's a bit like yesterday. Yesterday we saw that with the full shape of the galaxy correlation function, you can constrain H naught with similar kind of priors, right? And why is that? Because H modulates also the shape of the power spectrum. So, and this probes the shape of the power spectrum at the linear and nonlinear scales. And so that's the fact that this kind of, constraining H naught here is the fact that this is one thing, and also it's the shape of the power spectrum, and also the other thing, let me see if I have it here, is this one, no? You also have in front of this some terms that depends on H naught, right? So it does depend. It's also a geometrical effect to some extent. Yeah.
right. And this prior on the sound horizon, is it a Planck prior?
Yes, I think so.
Yes.
I think so. Yes. Thank you. Thank you.
Okay. Hi, everybody. Welcome to the last lecture of my series on this, the fourth lecture, dealing with fundamental physics with galaxies. And I'll jump right in. So what I decided to discuss today is I wanted to put galaxies discuss the interplay between galaxies and cosmology in a certain sense. And I will try to emphasize the connection to fundamental physics where I can. And as usual, I'm not very good at big reviews. I chose essentially two themes that I would like to discuss. The first one is the point that dark matter is kind of dark. Why do we even call it dark matter? You ought to ask yourself this question, how dark it really is, and where is it, why is it that we think dark matter is dark? In a sense, it doesn't interact much with other things. And the second thing is a certain connection between galaxies and the Hubble tension. And here, Matteo really, I think, helped me a lot in presenting some of the formalism, so I can skip quite a lot of stuff, which is excellent. I also had a subtitle for item number 2. I called it, I tried yesterday several times to pronounce this correctly, according to British pronunciation, for example, but decided not to go for it in the talk. Anyway, that's the subtitle. Matteo also mentioned this. So dark matter is kind of dark. And, well, you think that when you look at pictures like this of Andromeda galaxy, for example, and we saw in the first lecture that there is a lot of mass around Andromeda over here. And so, okay, dark matter is dark. We don't really see it. But then again, if you also remember, when we discussed Andromeda and the dark matter and baryonic budget in Andromeda, we estimated what is the dark matter mass to baryon mass for Andromeda inside, for example, R200, somewhere around here. And the answer for this ratio is in the ballpark of 10. Okay, there is about a factor of 10 more dark matter than baryonic matter. And how did we estimate the baryonic matter when we did this exercise? We looked at the light. The light is this tiny little spot here for Andromeda, and that's where this 1 part in 10 of total mass that is associated with stars came from. But then again, you guys, you know what is the cosmological average ratio between dark matter and baryonic matter, right? What is it? What is it in cosmology, on average in the universe? 1 in 5 or so, exactly, thanks. So what is going on here, right? We are finding somewhere in the ballpark of 1 part in 10 baryonic to dark mass ratio, whereas we know, well, if lambda CDM is correct, we know that if we would have gone even further and further and further away, suddenly, somehow, there should be more baryons over here, right? So in fact, the baryons that we see are at most half of the total baryonic matter that should be associated with this overdensity, right? Where are the remaining baryons? And this issue comes back in many different contexts. Why am I bringing this up now? I'm bringing this up because, okay, so we know there is more baryonic mass around here. It might be at somewhat larger scale, but there is a lot more baryonic matter around. We know it. It's not a guess if lambda CDM is correct. It's there. We also see it in BBN. We see it in the CMB in various forms. So it's there somewhere. Okay, so baryonic matter can also be dark, right? There is a lot of baryonic matter, and you don't see it. Okay, so it makes sense to ask ourselves a little deeper. If baryons can also be dark, why do we call dark matter dark? What do we really mean by that? So of course, many people thought about this problem and tried to play with various things. Let me take one very simple example, I think, that we can understand. And so suppose, for the purpose of the game, that actually dark matter particles could collide with protons. They do interact, for example, with protons and other nuclei, with the cross-section sigma chi p. Let me call dark matter chi and protons are p. Okay, let's suppose that this is the case, and in fact, perhaps our direct detection friends should be very, very happy. They may see it at some point, perhaps not, I don't know. But suppose these things can interact. Maybe another motivation to consider this kind of possibility is related to observational properties of galaxies, or as pointed out by Renzo Sansicci at some point, and emphasized by other people. And some people call this phenomena Renzo's rule. And the claim by these authors is when you look at many, many different disk galaxies, and you look at the rotation curves, then the claim is as follows. If you remember, again in the first lecture, we tried to crudely model the mass budget of galaxies, and some galaxies had both stars and gas. The stars usually live mostly in a disk, and the gas is in some configuration that you can roughly observe. And what these authors are saying is that for every disk galaxy that they have looked at, they presumably can do the following exercise. They can take the dashed curve, which represents, essentially is proportional to the rotational velocity induced by gas in the galaxy. The faint solid curve is the rotational velocity induced by the disk of stars. And now these distributions have shapes. You might not know their exact mass, but you know how much light there is. You know the profile of the light. What these people are doing, they're claiming that if you allow yourself to just scale arbitrarily the mass-to-light ratio of the baryonic components, the gas and the stars, with this kind of scaling, this scaling has two free parameters, just the normalization of these curves, the mass-to-light ratio. The shapes are fixed by observations. You can basically fit every disk rotation curve. You can judge for yourself to what extent you're going to take this seriously, to what extent there is information in these rotation curves, but this is taken seriously by many people. And so it kind of begs the question, maybe actually these people are saying that rotation curves trace light. Of course, this is the Mond paradigm, right? This is, if there is something like Mond around, that's the claim to fame. Rotation curve actually trace light, even though we think there is very little mass attached to the light, okay? So maybe rotation curves trace light, like these people say. Maybe light traces rotation curves. Maybe there is some distribution of matter, and the gas, dark matter, and the gas in the disk interacts with it and somehow responds. So maybe this could be a motivation to consider this kind of process even more excitedly. I'm just throwing this out there as a motivation to discuss this. Okay, so let's estimate. Can dark matter really interact with protons, and to what extent? Okay, so suppose the dark matter particles can collide with protons with this cross-section. Now we know, observationally, if we believe our analysis of rotation curves, we know the mass density of dark matter. That's the one thing we think we know to a reasonable extent. I'm not going to care about factors of 2 in this exercise. So we know the dark matter mass density in a galaxy like Andromeda, somewhere in here in the middle of the galaxy where we would live if we were in Andromeda. And I'm taking the numbers from the Milky Way. They are essentially cousins. Now, the number density of dark matter particle is just the mass density divided by the particle mass. So it's rho over m. And so the mass density, if dark matter particle mass is 1 GeV, for example, the mass density is 0.4 particles per centimeter cubed. Okay? Now, a proton that is moving around in the disk of the galaxy, this proton would have one collision with a dark matter particle in time t if that time is proportional to the mean free time between collision, 1 over sigma v, right? And so the number density is just m over rho, so the collision time is of order m over rho sigma v. Okay, that's the kind of estimate that I want to make. So a proton, another way to say it, a proton would have one collision with the dark matter particle in the age of the galaxy, about 10 gigayears, if I invert the formula, the ratio of cross-section to mass for this process is 1 over rho vt. Now on the right, everything is observable. T is just the number that I put there to check the relevance. So if the cross-section is in the ballpark of 0.4 barn per GeV, you're going to have about one collision in a gigayear. So now, some of you, the inflationaries in particular, are asking themselves, okay, so he's talking about 0.4 barn per GeV. What does it actually mean? How does it relate to our physical reality? Sorry, inflationaries, I have nothing against you. I just like to taunt you. So, okay, so let's put this on kind of a mundane scale. So for comparison, let's look at nuclear kind of cross-section, proton, nucleon, proton, proton cross-section. So at low energies, somewhere around here, hundreds of electron volts, proton-neutron elastic scattering cross-section has sigma over n in the ballpark of 20 barn per GeV. So that's somewhat like a factor of 5, or a factor of tens, actually. A few tens above what we would need for this collision. So nuclear collisions are stronger than this collision we have. However, this is an anomalously large cross-section in the sense it's actually mediated by a nearby resonance, which is the deuteron. Let's look at some other random process, proton-proton collisions. Definitely strong interactions, whatnot. Well, I'm plotting some LHC data at GeV energies. This is in the ballpark of 40 millibarn. Okay? In bottom line, this 0.4 barn per GeV is somewhere in the middle between kind of ordinary, mundane nuclear interactions. Not very dark. Okay? In other words, the galaxy is mostly nothing. It's mostly empty. You need a pretty large cross-section to have some effect there. Okay, so we put a scale on this number. However, the thing that really forbids us from making this exercise, from making protons interact a lot with dark matter particles, is essentially cosmology. Because in cosmology, there are some calculable processes. Galaxies are complicated. There are things that are difficult to calculate. Things like this Renzo's rule is not going to be easy to establish in simulations. It's interesting to try, but it's going to be hard. But cosmology solves this neatly for us, I believe. Because, okay, so we did this exercise in the galaxy today. Well, we can also scroll time backwards a few gigayears and do the exercise in linear cosmology before galaxy formation at high redshifts. So at high redshifts, we can ask, protons were also flying around in there at high redshifts. So how often did protons collide with dark matter then at the early universe if they are colliding with dark matter here today? So again, what we have, the time between collision is 1 over n sigma v, right? And n is m over rho. But now we have a little trick, which is there is in fact a machine here, the universe actually, that is controlling the kinematics of our collision. It's controlling v. V is the typical collision velocity, the relative velocity between the colliding particles. And that's a fun thing. So what I'm doing here, I'm replacing the relative collision velocity of our dark matter and the proton by just the thermal velocity of the proton. Right? I'm going to take this expression to relatively high redshifts of order 1,000. At high redshift, there is an irreducible contribution to the velocity at which particles are moving around. I don't know what dark matter is doing. If it's heavy, it could be pretty slow. If it's very cold, it could be pretty slow. But protons, I know what they're doing. They have the same kinetic energy. Thanks. Is it okay? All right. Okay, so protons are moving. You cannot stop them. They're moving at least at the thermal speeds. And so I'm just going to replace this speed by the thermal speed, which is T over m. And that's very nice. Why is it very nice? Because if you think about the particle physics setup, this is quite a unique scenario. What we have here, imagine that we have a situation that we're trying to calculate the effect of collisions of different particles here, protons and dark matter. Now in particle physics, suppose that the interaction rate, this cross-section I'm talking about, could be some arbitrary function of the velocity. For example, it could have some resonances. It could go like Rutherford cross-section, like 1 over velocity to the 4. It could blow up at very small velocities. Or maybe it could be suppressed at high velocities. There are many different scenarios different particle physics scenarios that I could imagine, where the cross-section would have some interesting structure. And so it's lovely that the universe is actually scanning the kinematics for us, because the universe is scanning the typical collision velocity as we go to higher and higher redshift. Okay? The velocity goes up like the square root of the redshift because it goes up like the square root of the temperature. So for comparison in particle physics, this is, for example, the plot from the Ting paper of the discovery of the J-psi particle. It was a painful and painstaking job to scan the E plus, E minus center of mass collision energy until you hit the structure of the cross-section when there is some new physics, some interesting thing happening. And so they had to scan painfully this collision energy going step by step in energy beams. For us, the universe is doing it automatically, okay? Regardless of the structure in velocity of your cross-section, the universe is going to go there and check it for you. So that's quite useful. So cosmology doesn't like it, and the natural thing to ask in cosmology is not really the typical time between collisions, because we want to know, do these collisions affect the thing we know how to calculate, which is linear structure formation, linear theory, linear cosmology at high redshifts. And so what we care is the number of collisions per dynamical time. Also for the Milky Way, I was asking the number of collisions per 10 gigayear per the age of the system. Here I want the number of collisions per Hubble time, which is 1/th. And so the Hubble parameter is just roughly, I'm assuming radiation domination here. I'm going to take it very quickly above matter domination. So Hubble parameter is roughly this. It's proportional to t to the 4 over m Planck. And this object over here is the same thing I wrote before. It's just 1 over the time between collisions. And I can put the numbers, okay? And the prefactor, so to scale the numbers, I write on the right the cross-section per unit mass that I needed in order to make some interactions in our galaxy in 10 gigayear. That's the number I have here. I scale, I keep track of all the redshift dependence. Look, density goes like redshift cubed, and temperature goes like redshift. You collect the powers, you have redshift to the 3/2, and I get the prefactor. And now there is a reason that I chose this 10 to the 6 here. Why did I choose 10 to the 6? Do you know what's the temperature of the universe at 10 to the 6? Redshift of 10 to the 6, who knows? Who knows what is the temperature, mean temperature of particles in the universe? Standard model particles at redshift of 10 to the 3, around the time of recombination. A bit less, so 0.2 electron volt or so. Exactly, so because of the large amount of entropy in the universe, of course, the temperature drops by about a factor of 10, which is the log of eta, beyond the ionization energy of hydrogen before you recombine, exactly. So it's around, temperature is around 0.2 electron volt when the temperature is 1,000. So the temperature is about 200 electron volt when the redshift is 10 to the 6. And so, okay, so this temperature corresponds to what velocity? I have 200 electron volt. I need to take the square root of this divided by the proton mass. So I have square root of 200, 10 to the minus 9. Proton mass is 1 GeV, or 10 to the 9 electron volt. And this maps to around 130 kilometers per second if I map this temperature to velocity. So I chose to normalize things by a redshift of 10 to the 6 because that is roughly the moment in cosmic history when the universe produced collision kinematics that are very similar to the collision kinematics that would be relevant in our galaxy, for the proton in our galaxy. Now, as an aside, if what I was asking was not collisions in a galaxy like ourselves, like Andromeda or the Milky Way with velocities of order 100 kilometers per second, but if I was interested, for example, to understand constraints on galaxy clusters where velocities can be thousands of kilometers, well, then I just need to scale my temperature to slightly higher redshift. And I will reach velocities of 1,000 kilometers at redshift of order 10 to the 8. Harder to constrain, but still interesting. If I was interested in about 4 NUCs here, collisions of gas with dark matter in, say, 4 NUCs in galaxies with 10 kilometers per second, I would just go down to 10 to the 4 in redshift. So universe tests all these systems. And the point is that the number of collisions per Hubble time in my model is very, very high at this redshift. And so it can be constrained. And so this is a table from one of these papers. And the entry that I highlighted shows the result, the constraints from linear cosmologicals from CMB and Lyman alpha forest data on collisions with the velocity-independent cross-sections. That's what I'm showing here. And we made this table such that on the last column, the number I'm writing gives in megaparsec the mean free path, the lowest possible mean free path that protons would have on dark matter in the Milky Way today. And this mean free path is around 100 megaparsec. Protons must fly for more than 100 megaparsec before they meet dark matter particles in our galaxy, because otherwise they would spoil the success of linear cosmology. Now you can compare this 100 megaparsec to the actual distance that protons do fly in our galaxies when they're circling. Well, they have lived for about 10 gigayears, right? They're moving at 200 kilometers per second. You do the math, they've only flown for about 2 megaparsec, which is just a few circles around the Milky Way. We discussed this, I think, in the first lecture. You don't really circle that much in the age of the universe. Point is, this is much, much less than the mean free path. Protons could not have interacted with dark matter particles over 10 gigayear. But because of the fact that cosmology scans many different velocities, in fact, I can constrain much more broadly. I can constrain many different dependencies of the cross-section in the velocity. The only thing that happens, because I chose my reference redshift to be the same redshift at which the kinematics at 10 to the 6 was the same as the kinematics in the galaxy today, I can repeat the same exercise for arbitrary cross-sections. The prefactor here would change. You see, you get this plus n from the cross-section non-trivial dependence on velocity, but the prefactor is normalized to be around 1 at redshift equal 10 to the 6, so it doesn't matter. And the number here in front is only going to change by under 1 amount, coming from some integral that you can read in the paper. Okay, so this constraint is much more general. There is another way to present it that I think is illustrative. What this plot is showing is, again, the number of collisions per Hubble time as a function of redshift. Each line here represents different parametric dependence of the cross-section on velocity. So for example, the black line would be like Rutherford scattering, 1 over v to the 4. And the red line is a velocity-independent cross-section. And the common thing of all these curves is that they are normalized to have of order 1 collision per the age of the universe in our galaxy. So regardless of the functional form of the cross-section, they all meet, because of this calibration, they all meet around redshift of 10 to the 6, and they have hundreds, if not thousands, of collisions per Hubble time. This is completely bad for structure formation. This is more or less like taking a hammer to Matteo-Ville Lyman alpha forest data. You don't want to do it because it's too nice and his data is really good. So we really can't have this kind of interaction, and we know it from cosmology. As an aside, for a comment to particle physics, for example, there are many interesting constraints. For example, this calculation shows, and there are many refinements to this in later years. You can find some reference in previous slides. It shows, for example, the dark matter particles, if they do have an electric charge, it has to be very small. Okay, so if dark matter particles have some small charge, epsilon times the fundamental charge of the electron in the standard model, this epsilon is very small. It's smaller than about 10 to the minus 6. Okay, so dark matter, if it is electromagnetically charged, it's very feebly charged. And there are some papers that can produce this thing by mixing another U1 with the standard model hypercharge and so on. So it's quite interesting. Okay, so I'm done with the first example. And I'm going to the second, galaxies and the Hubble tension. And again, this is what Matteo discussed this, which is great for my purpose. So the universe is expanding, as you know. And you also have seen that the expansion, of course, is driven by mostly dark energy and dark matter. And the simplest effective theory that we can write is just lambda CDM, where dark energy is a cosmological constant. But this is obviously just an effective theory. And moreover, this effective theory has some extremely puzzling features. Some of them are the big fine-tunings you know of. Here is another funny feature. The dark matter to baryonic mass density have a ratio of about 1 part in 5, as we just discussed. Why 1 part in 5, right? We don't know what the dark matter is. It doesn't seem, it's not any of the standard model particles. People are talking about crazy ideas like ultralight dark matter and so on. But why, if dark matter is some funny thing that doesn't relate to the standard model, why are the mass densities so related, right? Why, if one thing is a fly and another thing is a planet, their masses would be completely different. Why are these things the same? Their masses seem to be similar, the mass densities are similar, maybe there is some relation. Just another puzzle, there are many. So nobody would be really shocked if lambda CDM cracks open and breaks down and we find something new. And from this point of view, the H0 tension is very promising and I think very exciting. And what we have here, as Matteo discussed, we have what seems to be tension between two independent measurements of the Hubble expansion rate H0. On the left, I put the CMB, and on the right, I put the supernova type 1a. Now, I'll discuss in a moment that there is no expansion measurement with supernova. Of course, supernova are part of a distance ladder method, so you have to say what did you use to calibrate the supernova with. So here I write Cepheids, some calibrator. Okay, but you have these two measurements. They both have relatively small error bars, and they really seem to disagree. They don't like each other. Now, it's possible that there is some B lambda CDM solution to this and BSM solution to this. This is a paper that describes many different solutions. I only put the class of solutions that the authors describe as excellent solutions. I think my favorite is elaborated vacuum metamorphosis, but you can choose your own. And the first thing that comes to my mind when I think about this is one of my favorite caricatures from the far side, which is called Nature Scenes We Rarely See, which you can take in different directions. So the first direction also relates to what Matteo was saying. Many of these theories, they can happily hop above the obstacle, but usually they will encounter some other obstacles when they do that. That's on one hand. But on the other hand, nature is already bizarre, crazy, and amazing beyond comprehension, right? It actually has produced living combination of atoms that look like a deer, and it has also produced trees. Both exists. In fact, it's likely that sometimes situations like this are happening. So maybe this is in favor of one of these solutions. I don't know. What I will do, faced with confusion, is try to understand the data, and I will also try to make a connection to galaxies. So first, also Matteo said that CMB and large-scale structure, on this issue, they really seem to be in love. Independent determinations of H0 from this method yield results that are very compatible. So if you want, CMB has brought a good, strong friend, and they're both standing on the left-hand side. But then supernova did the same. And in fact, the supernova also used to have a very good friend, and this friend is strong galaxy lensing that Matteo discussed. And the measurement, as of 2019, was very compatible with the supernova measurement. And in fact, it was also competitive in terms of measurement error. And what would be very interesting for me is that this lensing measurement has everything to do with galaxies. This is about galaxies, whereas the others are really cosmological per se in some sense. So naturally, I'm going to focus on this for this lecture. Before I do it, just to remind you, a comment about the supernova measurement. This is not at all a criticism. This is just something to remind. So Matteo also showed this plot before. That's another combination of the same data, H0, and the different measurement from Wong et al. From 2019. The thing I'm surrounding here in green is the supernova measurement from Shoes 19. This measurement has been refined and improved, but didn't really change until as of today. So the error bars shrunk a little bit. The central value is essentially the same. And this beautiful plot from the detailed papers by the Shoes collaboration and Adam Reith is really useful because it reminds you that supernova are a classic distance ladder measurement. Okay? Supernova cannot measure H0 by themselves. What supernova data can do, they can measure very well the shape and the slope in a chunk of redshift where you have this supernova data. So they can measure the slope, but they never measure the absolute calibration. You can shift this curve up or down. It's a parameter of the fit. There is no theory expectation. There is no way to measure it, apart from calibrating it to the previous step of the ladder, which has exactly the same issue, and you need to calibrate to the previous step of the ladder, which makes the analysis very difficult and interesting, and sometimes prone to controversies. So for example, a different attempt to calibrate the period luminosity relation of Cepheids, for example, if you shift any step in this distance ladder by a few %, you shift them all. This propagates naturally. This is completely systematically correlated. And so there are many discussions about every step in this distance ladder. This is not a criticism. This is just to point out that that's the kind of difficulties you're going to need to face to convince yourself. Maybe we are convinced. Maybe this measurement is okay. But that's what they have to go through. Then there is a contrast with the lensing measurement, which is very promising, because the lensing measurement is not a distance ladder measurement. Instead, it's a one-shot measurement. Presumably, if you have a system, if you have data like this, strong lensing data like this, you get H0 with one system alone. Of course, if you have several, you combine, which is what the experimentalists did. And as of 2019, these measurements agree. But also, Matteo mentioned that later on, there was a revision, actually, in the lensing measurements. What was shown in previous lecture is that the error bar grew, okay, from TD Cosmo 1, the first measurement of this consortium that I summarize here, to TD Cosmo 4. In fact, we progress in time, but error bars increased. But there is another thing. In fact, if you take the nominal largest data set or optimal analysis they have, also the central value moved. So suddenly lensing and supernova disagree. Of course, this is no more statistically or systematically convincing the error bar is large, but that is the process that we've had. And I would like, in how much time do I have? Okay, I have plenty of time. So in around 10, 20 minutes, I would like for us to make it very clear what happened here. So you'll go out of this lecture really understanding what is happening here, what are the challenges, and what is promising about the situation. So I would like to remind us the following thing. First, how does lensing measure H0? This was already mentioned in the previous lecture, but we'll see it from some slightly different perspective. Then I'll remind of a challenge in the modeling. This challenge is the thing that caused the first analysis of the collaboration over here to move to the later one. And then I'd like to emphasize opportunities for galaxies and for fundamental physics. And even before I go to details, let me really stress that there are, I think, huge opportunities. And this field of galaxy, strong galaxy lensing is very, very promising for cosmology and for galactic structure also. That's the part that's maybe less emphasized. Because the analysis I showed before, the TD Cosmo and Holy Cow analysis, they were using 6 or 7 strong lensing system to measure H0. With LSST, they are expected to have in the ballpark of hundreds of systems, which is an enormous increase in statistics and in ability to check systematics. So this is going to be very, very exciting. Hundreds of multiple imaged, strongly lensed systems with time delays. Okay? And thousands if you remove any of these restrictions. And with JWST, of course, there will be improved kinematics and improved imaging, which will be very important, as you will see. So it's very promising. To remind what they're doing. So we have an extended source image, and we have a time delay, delta t, that Matteo already described. Time delay is simply these quasar images that you're seeing here. They have a light curve that is changing with time. You get essentially copies of the same light curves shifted in time, and you can find the time shift, supposedly. There are some challenges related to microlensing in this time delays, but hopefully they can be overcome and you can measure it. Now, the structure of this imaging is basically dictated by a geodesic diagram like this. So we have a source somewhere. We have a lens galaxy in the intervening distance. It's this orange little dot of a point over a patch over here. That's the lens galaxy. And we see more than one image, usually 4, because usually these lens galaxies are not just dumb spheres. They have elliptical shapes, and so they make quad images. And we also see little arcs over here. The arcs are real. So the points are point sources. The fact that they look very large is just because they saturate pixels around them. The points are really quasars that are point sources, but the faint arc around this is real information from the galaxy that is hosting the quasar. And we have in the ballpark of 10 to the 4 pixels, typically with the HST image of this. This could be improved with the JWST, hopefully. And like Matteo said, this image comes about essentially from a lensing equation like this, where kappa is the convergence. What is the convergence? It's a function on this map, on the image plane. Theta is the two-dimensional vector on the image plane. And this function simply gives the column density, the line of sight integral of the density of our lens, okay? So just the line of sight integral of the total density, that's sigma, divided by a cosmological factor, sigma critical, with dimension of surface density, and this cosmological factor actually is proportional. It scales like an inverse angular diameter distance. So in fact, this factor already scales like h0. It would have been beautiful if we could just directly measure this factor. Alas, we can't. We cannot directly measure this factor because in front of it in the numerator comes the surface density, and we never know that exactly to the level that we're trying to get h0. Otherwise, we've been done here. So what do we have to do? We have to combine information from time delay. And how do we do it? We take or how do they do it? They take the imaging data and they try to find the best fit. They're trying to solve the reconstruction problem, finding a fit for the function kappa that reconstructs the imaging. Once you've done that, once you've got a model for kappa, you can calculate the other objects like psi, the lensing potential, related in this relation to kappa. And in the same time as you're looking for a model for kappa, you're looking for a model for beta, which is the presumed source position. It's this vector here. This is beta. It is unobservable by itself. It's part of the modeling. Bottom line, these objects, beta and psi, are dimensionless objects. If from the imaging you are able to convince yourself that you got kappa right, then you can get beta and psi. And with beta and psi, you get this dimensionless tau, dimensionless time delay. The full time delay, this here is observed, is proportional to the dimensionless time delay with this proportionality factor d. D is another cosmological factor. It's the time delay distance, scales like angular diameter distance. So d is proportional to 1 over h0, and that's how you're going to go ahead and do this. Oops. Yes, so from the image you get kappa and beta. From kappa and beta you get tau. From tau and delta t you get angular diameter and you get time delay distance, and from this h0. That's the plan. Now here's the problem, and I'm at the challenges. The problem is the mass sheet degeneracy that Matteo mentioned. This transformation or this reconstruction is never unique. And what stands in the way is really fundamental. What stands in the way is that we're doing something funny here, right? We're trying to reconstruct the time, or essentially the time delay, the geodesic time delay, from the imaging map. But the real logic in Fermat principle is kind of opposite. Images will form where time delay is extremized. Images form, in other words, you could just, if you have this tau from this formula and you just take the gradient of this formula and equate it to 0, you obtain the lens equation. This is how physically the lens equation occurs, right? It's basically occurs at zeros of the gradients of the travel time. But zeros of the gradient of the travel time will be there regardless of the normalization, overall normalization of the function. Okay? So imaging information can never, ever, as a matter of principle, tell you what is the normalization of time delay. All they can tell you is where are the zeros, where are the extrema. So, in fact, imaging and time delay can never measure h0. It is simply not possible. There is an exact degeneracy. This degeneracy comes about because of the normalization of tau. The normalization of tau is exactly h0. Okay? So, in a way, this program would be doomed if there wasn't an external information that you could try to use to save it. Here I'm just flashing some formula, both for people who are afraid from formula that are too simple, and because I just want to make a comment that this degeneracy is true also at the level of the shear, right? I'm just talking about convergence, but shear, all the detailed angular information, the curl component and so on, is equally degenerate. It's all degenerate. In fact, there is a threefold degenerate, not just one degeneracy, because this transformation can happen at different places along the line of sight, and there are even generalization of the transformation, but it's essentially what I said. It's an affine transformation of the lensing system that leaves the extremal point at the same place, but changes the normalization of tau. So that's what we're facing. This picture illustrates it. In the simplest realization of this mass sheet degeneracy, it looks like this. Suppose I have a lensing reconstruction problem, so I see the images, and I have some model of the lens and some model of the position of the source. This mass sheet degeneracy is equivalent in its simplest form to taking this model and replacing it by another model where I have a little bit less mass in the deflector, in the lens. The position of my source is slightly different, it's scaled down, and there is this thin screen of mass in between. There is absolutely no way from imaging data to tell apart this model and this model. Unfortunately, they have different convergences related by this nonlinear transformation. Unfortunately, H0 changes by this transformation parameter lambda. This parameter lambda is just a real number, in our case small, of order 0.1, and it is essentially how much mass there is in this thin screen. Okay, so that's how it looks like. Now, you look at this thin screen and you're saying to yourself, or you should say to yourself, this is complete nonsense. Reality does not take galaxies and puts a thin screen on top of the galaxies, right? This is complete nonsense. But we are working here in a thin screen approximation. It's relevant for us, which means that you only care about the projected mass distribution along the line of sight. Your thin screen can actually come from very different scales in the problem and just be projected. All you need is that this distribution of mass have small gradients kind of on the angular scale of where the imaging information is. So it can also come from cosmology. If our source is somewhere, some gigaparsec away, and we are here, and we have the main deflector, then this main deflector lives in the cosmic web, and weak convergence and shear will contribute, in fact, effectively to this mass sheet. They will act to leading order as a contribution to the mass sheet. And the collaboration is, of course, perfectly aware of it. They have dozens of, and they and many others have dozens of papers. It's a major challenge that they are working to resolve this external, so-called external convergence or external mass sheet degeneracy from numerical cosmological simulations. And in this plot, I won't get into details, but they show to you that this is important. This is really important. This is kind of the relation of H0 that they would find as a function of this cosmological convergence if they didn't try to correct for it. Okay, there would be a very noticeable bias of H0. 50, you mean I'm done with 40 minutes by now? 10 more minutes, okay. So you will see this linear correlation, which is just the mass sheet degeneracy that they have to correct. They do it essentially on statistical basis with numerical simulations. Let me assume that they do it perfectly well, that they actually can take care of it. Nevertheless, they have still a very difficult challenge, but also an opportunity. And the problem is, these procedures are trying to fix the external convergence, weak cosmological convergence. But it is much harder, in a sense, to correct for degeneracies that are local to our galaxy. Now we're at the galaxies that we know and love. And so here is an example of this idealistic mass sheet degeneracy that doesn't look very sensible. However, if you ask yourself, okay, suppose that instead of adding an infinite sheet of mass, that looks very bizarre, I'll just add a small sheet of mass. All I need from this distribution of mass to do, I need it to be distributed on scales that are larger than where imaging information is. Then what do I get? Do I get a mass sheet degeneracy? No, you don't get a mass sheet degeneracy, but if this is large enough, you get an approximate mass sheet degeneracy, which is as good as you need. And this now you can make very physical if you just take it and rotate it around. And now what do we see? This mass sheet degeneracy can actually be approximated if our galaxies sit, for example, inside of some large-scale core distribution of mass. Okay, this will act for any intent and purpose, just like a mass sheet degeneracy, but approximate, as good as you want if you make it a bit big. So what you need to ask is, what is the scale of this thing that you need for our galaxies to resolve the H0 tension? So let's do the exercise. Here is an image from a real model, this DES 408, and the measurement from the collaboration for this particular specific galaxy, combining with no other system at this point, is this. It's very consistent with the supernova type 1a. It has a relatively large error bar because it's just one system at this point. And I'm literally plotting the convergence as a function of angle in arc seconds for the best fit model that the collaboration find for the profile of the system. What do I need to do? What damage do I need to do to this galaxy to resolve the H0 tension? Here is what I need to do. Okay, I need to mass sheet transform it, adding some core component, for example, or a very small component, and scaling down the density by a very small amount. And here I am, instead of 74 kilometers per second per megaparsec, I'm at 67, perfectly compatible with CMB. That's all we need. Okay? This is a big challenge, but at the same time, it's a very big opportunity, I think. Why? Because it brings back the spotlight on this boring little orange spot in the center of the system. Okay? We were trying to kind of ignore it, marginalize over it, but it doesn't want to be marginalized over. It doesn't allow you to do it because you really care about minute details of the mass distribution of this elliptical galaxy. You have to tackle this if you ever want to say anything about cosmology or age naught. We're back to galaxies and they won't let cosmology just move on. And so therefore I think it is natural that these lensing campaigns will actually focus at least half of their time, if you want, on the structure of galaxies. They provide really new sensitivity to galaxies, and that's exactly what the TD-Cosmo collaboration did in this fourth paper. Look at the title. This is no longer time delay cosmography. It's no longer the Hubble constant. It's now the Hubble constant and galaxies, okay? You cannot say anything about one without the other from this system. And what they're finding is interesting. The top results from this paper give you age naught of 74 with a very large error bar. That's the number that was shown in the previous lecture. But interestingly, they actually added more data. They added 33 additional lensing systems from the SLACS database. These systems have stellar kinematics, and they have strong lensing. What they don't have is time delay. So these systems by themselves don't tell you anything about age naught, but they help you. If they're similar to the original TD-Cosmo system, then they help you constrain better the profile of the lens. When they add these systems in the game, they get, in fact, their nominal pipeline answer, and the central value is now at the CMB. Okay? Error bar is still big, the degeneracy is still large, but we are at the CMB. However, the interesting thing about this really, apart from this shift, is that, look, we've done something here, okay? And this is sometimes forgotten. The fact that the best fit measurement went from 74 to 67 did not come without a price or without something exciting that comes along with it. It came together with potential hint for something that is really doing a mass sheet degeneracy in there. Okay? Look at that. This is a common constraint on the profile on age naught, if you want, and the profile of the galaxy. Lambda is exactly the mass sheet degeneracy parameter I was talking about before. That's how they implemented the problem in the pipeline. And they essentially have an roughly 2 sigma positive evidence for this kind of core in the galaxies they are analyzing. Now, I think personally this is slightly premature. I think that there are things that should be looked at more carefully, but this is very interesting. What came out naturally of the pipeline is actually positive evidence, perhaps for this object I was talking about. So I will just comment on this. This is work by Luca Teodoro, who is here in the audience. You can run some mocks with this lensing pipeline, and you can ask yourself, okay, all of this exercise I did before was just the lensing and the time delays. As I said, they cannot by themselves measure age naught. So what happens if we stop trying to measure age naught, we take age naught from my favorite source, it could be Adam Rees and supernova, or it could be CMB and LSS. Let's take a prior from age naught from somebody who can do it without degeneracies of that type. With that prior, what can we say about the shape of galaxies? Okay, that's part of the opportunity. And the answer you get by running these mocks is, without a prior, you reproduce what the collaboration did. In a sense, you get a measurement of age naught with a very large error bar per system. But if you add a prior on age naught, you basically obtain positive evidence for this core component, positive evidence for lambda. This evidence can be as large as 2 sigma per system, we think, with current CMB resolution. Okay, this has never been done, not in an official analysis yet, so I'm very much looking forward to see somebody actually doing this, doing the strong lensing analysis with the CMB prior, either from supernova or from CMB or both. Okay, so I'm almost done. A natural question to ask is when I'm trying to address this leg of the H-naught tension, the lensing leg, with this kind of galaxy profile, it's natural to ask the follows. If this is really the resolution of the H-naught tension from lensing, then it means that galaxies are non-minimal. There is some structure maybe in galaxies, there are maybe these cores. Then why would they be non-minimal, and why should these galaxies have a core component? I don't have a very good answer to this, apart from just why not? We don't know what dark matter is. We could think of several reasons for galaxies to have a core component. And the other thing we should recall, if the measurement is interpreted correctly as H-naught that is 74, the alternative to something like this is actually a breakdown of lambda CDM. Also exciting, yes, but these are two really exciting and positive possibilities. Either galaxies are very interesting, perhaps galaxies are very boring, and lambda CDM has just broke open. Okay, so that's where we are. But really, there could be very exciting possibilities. For example, perhaps we discussed the fact that ultralight dark matter likes to make these large-scale cores. Perhaps there is this kind of component of ultralight dark matter that is very light, 10 to the minus 25. I've shown you this ultralight dark matter miracle for the relic density with the same kind of parameters, F at the gut scale and M of this order, 10 to the minus 25. You can easily get naturally from vacuum misalignment 10 or 20% of dark matter being this dark matter. And then we expect that it will core around galaxies on very large scales because the mass is very small. And we think it could produce this kind of core components. This is just one example, which basically says perhaps lensing has found stringy axions. Okay, perhaps that's what we've found. It could be very crazy. Another possibility that we'll have to remember is that perhaps what we're looking at is really not precisely the effect of galaxies. This is this PG1115 system over here, and the collaboration is plotting it in a larger viewing angle. And so the lens galaxy, this one, that was really in the analysis, you can see it here, it's part of a group. It's part of a galaxy cluster, actually. Massive elliptical galaxies, like those used in this analysis, tend to be inside of a galaxy cluster. And so all the galaxies in circles are identified members of the cluster. And you've got to worry about this, because what does it mean? A galaxy cluster, like actual galaxies, has a large distribution of mass that is mostly dark. So all these galaxies are supposedly floating around in a very large overdensity of mass from a cluster. That would also act like a mass sheet degeneracy, and that would also be a tiny point from the point of view of cosmology, of large-scale structure. And so we and other people, I think, are analyzing now this kind of observations. For example, there are X-ray data and brightest group galaxies that we can try to use to constrain where the galaxy cluster really is, and can this actually take part in this H-naught lensing tension. Okay, so I'm basically done. I just want to point out what it means that LSST multiplies by 40 the number of systems. All these results of the lensing H-naught tension are from just these systems and another one, 7 systems. We're going to have in the ballpark 40 times more systems with LSST and with high resolution from JWST. I believe this issue will be solved. Either we find this evidence for cores, or these people nail down that there is a lensing agent measurement that is off from the CMB. So this is coming in your careers. It's coming in just the next few years. And I think it will be extremely interesting. Okay, so I'm done. This was my last lecture. I think it was quite clear, and well, you all knew it before, that astrophysics is intimately related to particle physics. Galaxies take a very important part in all of it. Not more special or more important than other systems, but at least equally important. And I hope you enjoyed it.
Hello. My question is a bit in this measurement of the shape of the galaxy that you had, basically putting a prior on H-naught.
Yes.
Okay, but I mean, I don't understand this very well because, I mean, if this shape of the galaxy and the measurement of H-naught are degenerate, I mean, then, of course, if you put a CMB prior, you're going to get a core, but if you put a supernova prior, then you're not going to get it, no?
Well, you will get something that tells you if all the lensing analysis is correct. There are no some hiding demons in there. If you put a supernova prior, it is telling you that galaxies are boring and they have nothing like this. That's what it's telling you. And lambda CDM is broken, which is cool and exciting. Why? Why is it broken? Because what is the supernova prior? Supernova prior is H0 74. That's what the supernova prior is. But CMB is telling you H0 of 67. So either some experimentalist is wrong, which I don't think is probably not the case, or we are not understanding something, or there is new physics going on. So it will also be very exciting, and we know the answer. Because boring galaxies is essentially the assumption that the collaboration took in the beginning. Okay, so this assumption will sharpen, if you want, and there will be some evidence for more evidence for the breaking of lambda CDM. But of course, you would not be able anymore to use the lensing data in combination with supernova to measure H0, right? You will be making a statement, elliptical galaxies are boring. That's what you learn, which could be interesting, but that's what you learn in terms of galaxy physics. Maybe tiny little comment on this is, as you saw in the SLACS analysis, there seems to be preliminary evidence at the level of 2 sigma that these galaxies are actually not boring, right? They see evidence from the kinematics that maybe there is this kind of core component. So maybe this kind of prior from supernova will actually be in some 2 sigma tension with the kinematics. But I think it's premature and needs to be done. My take would be, when this is done with real data, I hope soon, people will do both prior from supernova and see what it means, and prior from CMB and see what it means, and follow both and see which one is right.
Thank you for the lecture, very interesting. I have 2 questions actually. The first one is, I don't know, in the analysis of supernova, we saw that a peculiar velocity can give a systematic error. In the case of lensing, I don't know, can peculiar velocity of the background quasar give some impact?
That's a very interesting question. And I haven't calculated, and I'm not sure what the answer is. So basically, the way I would take what you're saying is that mismodeled peculiar velocity, if you dot it with the line of sight for the different images, could maybe enter into time delays through just the Lorentz boost, just a Doppler effect in a non-trivial way. I think the answer is no. I think the velocities are way too small, but we should do it offline. I don't want to say something incorrect. So it's an interesting question.
Because at which redshift are those quasars?
Order 1. So the quasars are at redshift of around 2 typically, and the lens is redshift between half and 1. Mm-hmm. And this will stay more or less the same also when the LSST will be there.
Okay. And then the other question was about this core component. If we have, so from string theory, we know that we don't have to have like a one mass for the dark matter. If we populate if we have dark matter and a different fraction of dark matter have a different mass, what is the expectation for this core structure?
Well, to be completely honest, I don't even know for sure what's the expectation with 1.
No, okay.
We estimated it, but this has not yet been fully simulated, and it can be simulated. I think it should be simulated. So the answer is we are not there. So if you want to it's a I would say theoretically viable possibility in the sense that if I have 1, like you're saying, why don't I have 7 or 700? But let's cope with 1 first. So I was just throwing a possibility there that we studied, but it is simplified and still need to be verified with the simulations. It was mainly to tell you that we want to understand what kind of lessons we can get from this kind of core. So short answer, when there are more than 1, I'm even less sure than I am with 1.
Okay, thank you.
Yeah, thanks for the nice lecture. I wonder, well, it's very hard to proc lambda CDM, but maybe it's a bit easier to somehow observe from a different perspective weirdness of the galaxies. Are there any other observables?
Oh, absolutely. Very good. So there are definitely other observables. I wonder if I have backup slides for this. Yes. So for example, I've mentioned stellar kinematics. This was stellar kinematics with SLAC systems. It's resolved, but only mildly resolved. These are still far away galaxies. So what you could ask yourself, and we asked ourselves in addition, is what about nearby massive ellipticals, right? We are seeing lensing by far away massive ellipticals, which are not well observed. What about nearby ellipticals that are observed? So stellar kinematics, basically dispersion measurement, is a very natural thing to do, has not been done at this point. What we have done is we have compared, so what you see here is the inferred density profile for some particular massive elliptical galaxies, relatively local massive elliptical galaxy. This is from Capillari et al. From this paper, as a function of radius. And the measurement is the green band. And what I'm showing here in blue is the type of profile that you would need to completely resolve the age knot tension with this galaxy. And in red, I would vastly overshoot by more than a factor of 2 the age knot tension in this galaxy. And this basically tells us that the data is interesting at the level of dispersion measurement, but as of now, even using local measurements, we are not at the level that we are sensitive to this feature, which also shows you why these strong lensing measurements are maybe so interesting, because they are sensitive. With an age knot prior, they are sensitive to just a few percent deformation of these profiles, where direct kinematics is not. So these analyses, I think, are very highly motivated and should be done. It's important to remember, when you do them, you should actually test the model. These analyses are model dependent. They're solving a Jeans equation that assumes some profile that you check. And this paper did not check a profile with a core. So this is essentially our constraints for families of models that are NFW-like. It is possible that if you would add the possibility of a core component, you can even nail it down to what it needs to do to solve age knot. If you do that, there might be significant positive evidence, or maybe negative evidence, I'm not sure. But so all of the analysis need to be redone. As of now, they're not fully decisive. And the previous slide was the Milky Way. Why look at ellipticals? If there are these cores, then I don't want to fine-tune for age knot. I am saying that maybe all massive galaxies have some, at the outskirts, some extra deformation. For the Milky Way, this deformation will be somewhere here, if I'm mapping the information from the lensing systems. This just so happens to be the case. The imaging information, if our Milky Way was the lens, so we were familiar with the system and we know to understand the scales, imaging information is on the region of the projected Einstein ring. So here it would be for the Milky Way, a few kiloparsec. By the way, a very complicated region. This is RS, parameter of the NFW fit of the Milky Way. And we know from the lensing already that these features from the core, they have to go at larger distances, somewhere around here. So again, challenging, but maybe not completely hopeless for other galaxies. So we're looking for a 10% deformation of this thing.
Okay, thank you. Yes.
Actually, I have a second question in this core thing, because I don't know if I understand well the scales and things. So as long as I understood, you say, so we are getting the structure of the galaxy as informed by dark matter simulations, right? So NFW would be like a cold dark matter, and then if you observe a core, would be maybe some other kind of dark matter. For example, you mentioned this ultralight dark matter, but I know that there are some other mechanisms like dark matter heating that are at least effective at least at dwarfs.
Right.
I don't know if it is the same thing for these these galaxies.
So the scales should be clear. Let me explain the scales. So let me break the question into two parts. One, both I'm sure shared by everybody. So the first is, what is the physical scale? When we look at these images, actually in this picture what I'm showing is the following. I'm showing, so this is a typical image. And this range where you see the arcs is of the order of what is called the Einstein ring. Einstein ring is the ring that you would have seen if the lens galaxy was spherical And if the source was sitting right exactly behind it, then you would see a perfect ring. The scale radius of the ring is called the Einstein ring. So this is Re. And when the lens is not completely spherical and the source is not exactly on it, you nevertheless, the structure you get is typically on the scale of the Einstein ring, but it's not exact ring. So that's the Einstein angle. And you can see it for these systems. It's summarized from the collaborations. Einstein angle for the systems we're talking about, it's of order 1 arcsecond. And these systems are gigaparsec away. You do the math. 1 arcsecond gigaparsec away or so is a few kiloparsec. So I can map it to the Milky Way. The Milky Way, that's a few kiloparsec. That's where the projected Einstein radius would be. So when you look at this galaxy, you see the light. Really where the images are, it's the heart of this galaxy, okay? There is a lot of stuff going on. You are around here if it was the Milky Way. You see a lot of mass beyond what you naively expect, for example, from dark matter. There are a lot of stars, okay? So there is a lot of business going on. So that's the scale of the image. What is the scale at which I need the core to be? This core is not an exact mass sheet transformation, right? It's not an exact degeneracy because it's not infinite and it's not a sheet, right? It's a core. So it's an approximate degeneracy. And so from the imaging resolution itself, there is a limit to how big this core should be. It needs to be very large in radius to not spoil, to be a good enough approximate degeneracy and not spoil the imaging. And so we know that the ratio between the size of where our big core is and the size of where the imaging is in the ballpark of a few. The core needs to be a few times further out. So it needs to be somewhere around here. That's where the core, that's a constraint from the imaging. So that's the scale. It's roughly the same situation for the massive ellipticals and for a Milky Way-like galaxy. So that's the scale where things are. Now, you're asking, could it be that it's not some very interesting non-minimal dark matter model that is doing this core, but maybe it's baryonic feedback? Very short answer is, maybe, I don't know. Maybe this is some kind of AGN feedback. But then, now it's again, a very interesting question, I think, for simulators, for example, to tell us if it's possible to produce deformations of the order of tens of % in the mass of the galaxy from feedback at scales of hundreds of kiloparsec, which could be a big challenge for this kind of models, but I think it's an open question. Regarding the inner part of the slope, the collaboration, at least, is not supposed to be very sensitive to these details. They are doing separate analysis. They are doing some analysis that assume an FW profile and combine this with the observed profile of the stars and kind of marginalize this. And other analysis that just assume an arbitrary power law profile that kind of supposed to include together dark matter and baryons agnostically. And these two analyses generally pretty much agree. The fact they agree may not be a shock. You see, for example, in the Milky Way, the rotation curve is nearly flat, or the mass is nearly a linear function of R, which would be a flat rotation curve. So somehow, by the way, we don't know how, dark matter and stars conspire to give you a nearly flat, what looks like a nearly flat rotation curve. So it works also for elliptical. So I don't think, but again, it's important to check how sensitive these analyses are to the details in the inner part. Okay, so I hope I answered.
Questions? Thank Akfiran again, and yeah, let's go for lunch.